So let's talk about those non-permissible values, because honestly, before you learn how to do any kind of identity proving, you got to be able to concentrate on those non-permissible values and just rattle them off really, really quickly. So remember, non-permissible values are when the denominators are zeros. Okay, those are why we call them NPVs. So looking at our first one, for example, tangent here. Tangent, rewrite it into something that's easy. I always like using cosine and sine, right? So you know that tangent is sine x over cos x. And immediately you can see, aha, I got a denominator, which means my cos x cannot equal to 0. Thinking about this, where is cos x equal to 0? Where on the unit circle is your value of x equal to 0? Well, here and here, of course, at pi over 2, okay, right? And 3 pi over 2. That makes sense, doesn't it? That's where the coordinates are 0, 1 and 0, -1. Ooh, really nice. There's your zeros. So obviously you would say in this range from 0 to 2 pi, you'll say, okay, it can't be. So x cannot be able to equal to pi over 2 and of course 3 pi over 2. But let's look at the obvious here, folks. If I was going to do a general formula that says these are all the non-permissible values over infinite values, you have to realize that, look, this is only a difference of, yeah, it's only a difference of pi. 1 pi rotation going this way, right? Or a pi rotation this way gives you back to the same point. So I can say that for our NPVs, we can say x cannot equal to, and I'll just pick the simpler one, pi over 2 plus the fact that I'm rotating this in any direction, either positive or negative, by a multiple of pi. So I have to put down that my n equals to the, of course, the group of i's, the integers, positive or negative, because I can go, in fact, I can go in the positive direction here, or I can go in the negative direction and get to my value of pi over 2. Okay, enough said. Let's keep on going. Look at this one. Oh, what a monster. Oh, what a monster. But what we look at is we say, okay, 1 minus tan squared x cannot equal 0. Aha. So bring the 1 over. You got minus tan squared x cannot equal to minus 1. And then, of course, negative negative makes this a tan squared x cannot equal to, yeah, positive 1. Inverse square root there, inverse squared, which is square root, giving you tan x cannot equal to plus or minus 1. Okay, so my question then is, where is tan plus or minus 1? Again, bring up your wonderful unit circle. There we go. You know and I know that that's that square one, right? This is going to be at, yep, pi over 4. Look at that. There's 3 pi over 4. There's 5 pi over 4, and then there's 7 pi over 4 way out here. So those are all the values you know where it can be, tan can be either plus or minus 1. Why? Because remember, those values are the same. Root 2 over 2, root 2 over 2, and if you're looking at y over x, root 2 over 2 divided by root 2 over 2, of course, is 1 plus or minus. Got it? Okay, so that means x cannot be, and if you want to write it out for all of these factors here, under the domain restriction of 0 to 2 pi, you can. You just list every one of these. But how about for a general restriction? A restriction across all infinites. Okay? Look at this. This is going to be start with pi over 4. And look, how do you go from pi over 4 to here? Look at that. Is that not just adding half a pi? Right. So plus, look at this. This is going to be pi over 2 times n, right? Absolutely. Case in point, if you want to prove it, watch. Just go pi over 4 plus pi over 2. Watch this. Common denominator, okay? Giving you pi over 4 plus 2 pi over 4, which gives you, guess what, 3 pi over 4, and there's your next spot, right? And you add again another pi over 2 to get to this spot, another pi over 2 to get to here, and so on and so forth. So you can actually write this out, of course, like this, pi over 4 plus pi over 2 times n. Don't forget to tell me that the n is a matter of the i's, of course, integers all the way. Now, look at C. This one's interesting as well. And I'm going to have to clean this up a little bit because, of course, I'm running out of room here. Look at C. C says I've got, oh my goodness, I've got secant x over tan x. So what? You're looking for non-permissible values. Take this tan x again and check this out. Tan x, you remember, is sine x over cosine x. So any one of these guys, either sine x or cosine x, will make this guy 0, right? And, oh my goodness, if it's 0, non-permissible. This one, if that's 0, you got automatically non-permissible because it's in the denominator. And this one, if it's 0, makes the whole thing 0, which makes this 0, which makes it non-permissible. Oh my goodness. Okay, so where is sine x cannot equal to 0, and where is cosine x cannot equal to 0? Think about it. Again, right? This wonderful thing down. You know and I know these are our quadrantial points. Here, 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 and here. So if you think about it, x cannot be equal to, yep, 0 pi. Look at this. Pi over 2. Right over here, pi. Right over here, 3 pi over 2. And finally, 2 pi. So can't be equal to all of those things. Go back and compare this with the initial domain. If you look at the initial domain, it did in fact include the 2 pi. So in your answer down here, you have to include the 2 pi this time. Watch for that because they sometimes put this down as 0, x, 2 pi, and you don't include it. If it was written like this, you would not include the 2 pi. But being that it's there, you have to include it. So now, next thing we're going to do is we're going to go out and do a couple more things. Watch out for example 3. It's a little bit tougher here. Okay, so let me clean this out, and I'll go to example 3 right away. Hold on. Oh, that looks nasty, doesn't it? Well, so what? You know you're just looking for the non-permissible values, and you're not solving this. You're not trying to find theta. You're not trying to do anything. All you want is the non-permissible values. So look, take this one and say 1 plus sine theta cannot equal to 1, or equal to 0. My apologies, 0, of course. Cotangent, do that one over here. Cotangent theta cannot equal to 0. Now start solving. Start solving. Bring the 1 over, and that's why I was thinking of 1 earlier. Cannot equal to -1. Where is sine theta -1? Again, unit circle time. Where is the y coordinate -1? Okay, it's got to obviously be one of these quadrantial points, right? So start writing down what the quadrantial points are. This guy, in fact, is 0, -1. You're at 3 pi over 2. So guess what? X, or theta in this case, cannot equal to 3 pi over 2. That's one of your restrictions. Now, look at this guy. This one's going to be cool because it's cotangent. Now, you know tangent is sine over cos, so cotangent theta, of course, is going to be cos over sine. Oh my goodness, how pretty is that? And you know, since it's in the denominator, that means cosine and sine cannot be equal to 0. So let's figure that out. Remember, just like we did before, cosine cannot equal to 0. Where is cosine equal to 0? Cosine's equal to 0 here and here. Well, we've got this point already taken care of, right? Okay, so that's fine, but we don't have pi over 2. All right, so let's add that to this. So theta cannot equal to 3 pi over 2, and of course, pi over 2. Let's keep on going then. All right, where else? Well, we have to deal with the sine thetas now. You know that sine theta cannot equal to 0. Where is sine 0? Oh, sine 0 is here and, in fact, here. Oh, okay, so that's at 0 pi, at pi, and, of course, 2 pi. So there's our other points. So let's put them in. 0, we'll put in front. We'll put, okay, there's pi over 2, there's 3 pi over 2, include pi, and of course 2 pi. Those are all our restrictions based on one rotation. Now, if you wanted to do all of the restrictions for, let's say, an infinite rotations, Again, think about what you're doing here. You're going from here to this point, from here to this point, from here to this point. All of those points on our quadrantial points on our axes are non-permissible. Remember, each rotation is just pi over 2. So you can say pi over 2 plus n times, yeah, pi over 2. Well, why would you say n plus pi over 2? Since it sounds a little redundant, doesn't it? So basically, this reduces down, very, very simple. This reduces down to pi over 2 times n. If you use 1, that's fine. If you use 0, you're here. If you use 2, you're at pi. If you use 3, you're at 3 pi over 2. If you use 4, you're at 2 pi, and so on and so forth. Don't forget to tell me that n is an element of I. So to properly write this, put it as theta cannot equal to, that tells it's a non-permissible value, and you're good to go.